Hello everyone and welcome to the Game Engine programming series where we write a game engine from scratch. Today we are going to start working on an asset editor class for geometry assets. We will also prepare for viewing a geometry asset by writing a MeshRenderer class. Let's start by creating a new type of editor, which is a geometry editor, to just examine any kind of geometry that we generate or import from a 3D file. Here in editors, I'll add a new folder called GeometryEditor. And in GeometryEditor, we will have a class that functions as the view model for the GeometryEditor view. Because this is a view model, it should inherit from viewmodel base. And because we are going to have different editors for different kinds of assets, we are going to have an interface defined for all of them. And I'm going to call it iAssetEditor interface. And for now, all I have for this interface is an asset property, which is a read-only property, and a method that we can call to set an asset for this asset editor. Now going back to GeometryEditor, we need to implement the property and that method. And by the way, I need to move this iAssetEditor to outside GeometryEditor folder because we are going to use it for other types of asset editors as well. So now we can have a property that's of type geometry. And because we are going to use the WPF 3D functionality, there is a geometry in there as well that will collide with our geometry class. And therefore, I'm going to remove this reference to the content. And then I can state here explicitly that we need the content geometry. And all this asset does is return a reference to this geometry. And when we set the asset, we check if the asset is valid. So it should be a geometry asset. Okay, now that we have this geometry editor, we can go back to the primitive mesh dialog and set its asset. Therefore, we are going to have a data context for this window, and that's a geometry editor. Of course, I need to use the right namespace, which is editors. Okay, and then here in update primitive, we can set the asset for the data context, which is the geometry editor. And what this editor does is to render this geometry, basically using the WPF's 3D renderer. So what I need to do now is to unpack the vertices in this geometry. And normally when we have our graphics renderer, we just send it to the renderer and it will render it for us and we can see it. But now that we don't, we need to unpack these further for the WPF renderer. And this is kind of a temporary solution to show what's in this geometry. Therefore, I'm going to create a couple of classes that will unpack these further and render them. The first class that we need is a class that will hold our unpacked vertex data. So we will unpack our vertices to their components, which are the positions, normals, and UVs, and we also need to use the index buffer. This class represents one of the meshes. And to display this correctly, we also need a material for it. And the way we do that here in WPF is to just use a brush. So I'm going to define two brushes, one for specular and one for the diffuse color. Here we have a really faint dark gray specular color, which makes this material look rough, so it's not shiny. Normally you don't want to put a brush in a view model like this, because a brush is a dependency object, which means that it belongs to the views, and you don't want to mix controls of your application with the view models of your application. As you can see here, it's a dependency object. So we don't really want to mix that. In this case, I'm making a kind of exception because, as you can read here, it's temporary. And the next one is for the diffuse color. And the default diffuse color is just white. Now that we have this class to contain the vertex data, we need a mesh renderer that would unpack the geometry into this vertex data and display it in the 3D viewer. Okay, here, because we are in a 3D scene, we need a camera that has a direction and a target to look at. So I'm going to define the properties for this camera. The point of this offset camera position is to offset the camera with respect to camera's target. So if the target point where the camera is looking is moving upwards, then the camera position moves with it. And that way we can move the camera with respect to the object that we are looking at. And because we are going to bind to this property, we need to notify the viewer that this property changed. And that happens whenever either the camera position or camera target change. So here we need to do one more onPropertyChanged event for offset camera position. And also we need to set some defaults for direction and position and the target so that we have valid values. I would like to position the camera somewhere in the positive Z direction, so it's looking into the scene. And the direction is the opposite of the position. And the initial target where we are looking at is the origin. Further, we are going to need some lights in our scene. So I'm going to create some properties that contain light information. Here I made a color that will be used for the key light, which is the main light in the scene, and it's a grayish, not quite white color. And then just to make it a bit more interesting, I'll create more light that represent light that's coming from the sky and light that's coming from the ground. So it gives the model a kind of fake global illumination feeling. For example, here I have the skylight and it has a bit of bluish color. And next one is the ground light. And this one is a bit of a warmer color that comes from the ground. And the last one is just an ambient light, which is a bit dim and neutral gray. And the last thing that we need to do in this class is just to have a constructor that accepts a mesh LOD and unpacks it into this MeshRenderedVertexData. Each time that we create a new geometry, a new mesh renderer is also created, but we want to take over the old camera positions and directions. So we use the old mesh renderer to copy those values. If you look at the vertex format that we are packing in the geometry, in vertex static, you see that there is some information in here that we don't want. For example, this tangent we won't use in the mesh renderer that we are writing right now. So we need to skip these over to get to the UV. And the purpose of the calculation that I'm going to do now is to skip over extra information that we are not going to need here. Here we have 3 floating point values, so we skip over 3 floats. And then we have 4 bytes, which is just 1 integer, so we skip over those as well. And then we have 2 normals. Those are 2 16-bit values, so we skip those. And later on, when we want to read UVs, then we skip tangents as well. And one more thing that I would like to do is to figure out what the bounding box of this object is that we are trying to render, and then set the camera in such a way that it will look into the front of the object. And to do that, I calculate the bounding box, but I also calculate where the average normal of that object is pointing to. So if this is an object that has a front side and missing polygons in the back side because it's situated against a wall or something, then we don't want to show it from the back side. We want to point the camera to the front of it. And we can guess by looking at what the average normal value is of all the polygons in this object. So first, to calculate the bounding box, I will need the minimum and maximum of the positions in each direction. And also remember that we packed the vertices in a kind of bit values. So we use this function to pack a floating point value in a 16-bit integer. Now we need to unpack these values. And if you look at this function, we need to do this unpacking of the floating point value between -1 and 1 in C# side. So basically we need to do this. We know that the minimum value is -1 and the maximum value for a normal component is +1. So this is I divided by intervals multiplied by 2 minus 1, because the value of minimum is -1. And what we can do to speed this calculation up in the C# side is to pre-calculate this part, which is 2 divided by intervals. And that's what I'm going to do now. Now we are ready to go through all our meshes and unpack the data. Information about the third component of the normals, which is normal z, was included in the second bit of this sign integer. So we shift everything to the right so that we get the last byte and then end that with this value. This is not strictly necessary, but it's just to be sure that everything except this last byte is zeroed. Here we take the minimum and the maximum values depending on the position. So if we find a vertex that is outside the bounding box, then we adjust the boundaries of this bounding box. Next, we are going to read the normals. This is the formula that I was just talking about. And now that we have the x and y components, we can calculate the z component. And this is also exactly what we are going to do in the vertex shader to unpack our vertices. Here is a straightforward calculation to calculate a unit value. So we know that the length of the normal should be 1. So we use this Pythagorean formula to calculate the third component. And we clamp it between 0 and 1 in case these values are a bit changed due to this packing and unpacking. And then we take the square root of that. Also remember that we packed the sign of the z component for normals in the second bit of this value. Now we have this vector 3D that we constructed using these values, and then we put it in the normals collection for vertex data. And because we are going to look at the average direction of all normals, we are going to also add it to average normals. Next, we are going to read the UV coordinates. Here is where we skip over the tangents, because we are not going to read those in. So now we are done reading all the data that we need from the vertex buffer. And next we need to read the index buffer. Here we need to read the buffer in, depending on the size of each index. So if we have 16-bit indices, we need to read 16-bit unsigned integers and 32-bit signed integers otherwise. So this is important because if you have a lot of vertices and the index values will become larger than it would fit in a 16-bit integer, we need to use signed integers because otherwise the values would be interpreted by this collection that we have here as negative values. So if you would put large unsigned values in this collection, it would interpret those as negative indices, and that wouldn't work, obviously. And then we are basically done unpacking the data. The last thing that we need to do in this function is to tidy up things a bit. Here I'm calling this freeze function to make the object unmodifiable. And that means that the framework can do some optimizations and it might become a bit faster. And to finish this, we just set the camera position and direction depending on how big this object was and the average of the normals. So if we already had a mesh renderer, we just take the old values for the camera properties. And otherwise, we will use the bounding box and the average normal value. This radius is the radius of a sphere that would enclose this bounding box. And I also multiply it by this random value of 1.2 to make it still a bit bigger. Here I am looking at the average length of all the normals. And if it's larger than this arbitrary value of 0.8, that would mean that there would be a bias towards a certain direction. And I take that direction as front of the object. So this is kind of a heuristic that I'm using. It might as well be wrong, but I'm just going to try this for now. So in there, if that's the case, then we normalize the average normal and take this radius and set the camera at that position. And if that's not the case, we just set the camera somewhere outside of the bounding box of this object. So this will result in the camera being in front of the object, at least in front of the bounding box, halfway up, and the value of radius is how far in the Z direction the camera is moved. And we still need to set the camera target. That's where the camera is looking at. If you think that this is the center of the object that we are rendering, then you have guessed correctly. That's where the camera is looking at. And that was all I wanted to do for this class. Now we can use it in our geometry editor as a property that we can bind to geometry editor view that we still have to write. So let's add a new property to the geometry editor that is of type MeshRenderer. And when we call this setAssets function to set a new geometry, then we also create a new instance of this MeshRenderer. And this object might have different level of details. And for now, we are just going to take the first most detailed level of detail to display. And later when we import objects that have different level of details, or we generate some kind of primitive mesh for which it makes sense to have different LODs, then we can also change the level of detail depending on where the camera is with respect to this object. But for now, we just take the first LOD. Now we are ready to create the renderer. Next time, I'm going to write a new control that will use this data and display the 3D meshes. Thanks for watching. If you like this video, please feel free to like and subscribe. If you join me on Patreon, you'll get access to the code on GitHub, so you don't have to type everything over from the video. Plus, there are also other nice goodies and rewards exclusive to my Patreon supporters. Please use the link in the video description to check them out. I hope to see you next time. Until then, take care and happy game engineering!